By bit, we are unlocking its secrets. We now know that our galaxy contains billions of other planets, but how can we learn more about them? What traits do these exoplanets have? What are they made of? What are their environments like? How have they evolved over time? Are they habitable? And can planets lose habitability over time? Imagine we could study one of these planets up close. We find one of similar size, mass, and composition as Earth. By all accounts, this planet appears very similar to our own. We discover evidence that this world may have once had liquid water oceans and volcanoes, a setting that could have been favorable to life. But over time, something drastic happened to this environment. This planet's sun grew brighter and hotter, increasing the temperature here to the point that the oceans boiled away. And then gradually, the volcanic gases created a thick atmosphere with clouds of sulfuric acid. That once friendly environment was gone. But all is not lost. The remnants of such a world may hold the key to understanding planetary evolution and habitability. The twist is that this isn't science fiction. This planet does exist. And if we want to learn more about the past, present, and possible future of our planet and the billions of similar exoplanets out there, this mysterious one needs more study. And it doesn't reside in some distant solar system. Truth be told, it sits right next door. This planet is Venus. And the more mysteries we can unravel here, the more answers we can find out there.
I'm Jay Herman. I'm the EPIC lead scientist for the Discover mission. On July 6, 2015, we released this spectacular image of Earth taken by NASA's EPIC camera. Now, we assembled more than 3,000 images captured by EPIC into a time-lapse sequence that shows a year in the life of our planet. EPIC is an Earth science instrument aboard the Discover satellite, which launched in February 2015. The spacecraft always remains between the Sun and the Earth, approximately 1 million miles away, at a special gravitational balance point known as Lagrange 1. From this view, EPIC sees the sunrise in the west and the sunset in the east at least 13 times a day. The haze, seen around the edges, is due to scattering of light by molecules in the atmosphere. Scattering is also what makes the sky appear blue during the day and red at sunset. The colors shown are our best estimate of what a human sitting at the location of EPIC would see. EPIC takes at least one set of images about every 2 hours. The camera records each set in 10 different wavelengths, at least 3 separate wavelengths, red, green, and blue, are combined to produce this color view. In March, the moon passed between the Earth and the Sun, causing a total solar eclipse. During the eclipse, the moon cast its shadow over a portion of the planet. If we slow the video down, we can see the moon's shadow make an appearance right about now.
When we look at Jupiter, we're seeing the top of its atmosphere and its weather layer. And its weather layer contains a lot of interesting features such as jet streams, vortices, storms, and these particular features called hotspots. So hotspots are like holes in the clouds because they appear very dark when observed in visible light, but in near-infrared light they appear very bright. This indicates that we're seeing deeper down into warmer layers of the atmosphere. Hotspots have been previously studied by the Galileo Atmospheric Probe. In 1995, the spacecraft released a probe that descended into Jupiter's atmosphere, specifically at a hotspot. And this probe made the first in situ measurements and the only in situ measurements of Jupiter that exist today. So it's very important to understand how hotspot meteorology works in order to place these in situ measurements from the Galileo probe in its proper context. In 2000, the Cassini spacecraft flew past Jupiter and created a series of still images that we compiled into time-lapse movies of Jupiter's atmosphere. Using these movies, we observed Rossby waves that caused north-south meanders in a jet stream south of the equator. With new movies, we instead focused on hotspots. Hotspots are unique because we believe that there is a Rossby wave similar to what we previously detected, but instead of this Rossby wave moving north-south, it primarily moves up and down in the atmosphere. The downward portion of the wave pushes air down into warmer layers of the atmosphere. This causes any clouds that are embedded within the wave to evaporate and prevents further clouds from forming. So at any given time, there are approximately 8 to 10 hotspots in Jupiter's atmosphere that are spaced roughly evenly apart from one another. We believe that each of the downward portions of this Rossby wave corresponds to the hotspots that we see on Jupiter. This new finding is exciting because it'll allow us to re-examine the Galileo probe data and allow us to better understand it and better place it in the context of Jupiter's overall global climate and atmosphere.
My name is Amy Simon Miller, and I study the atmospheres of the Jovian planets. Weather on Jupiter is confined to a rather thin layer, kind of high up in the atmosphere. So the tops of the clouds are what we're seeing when we look at Jupiter. One thing we're seeing in the southern part of the equatorial region is little V-shaped clouds or chevrons, and we wanted to understand how those are moving in the atmosphere.
What we think chevrons are simply holes in the clouds. They're simply areas where we don't see any bright white clouds.
The Cassini mission flew by Jupiter in the year 2000, and because it was a slow, distant flyby, we got a lot of coverage of the planet over a long time period. So we were able to put those images together and make movies. What we found by looking at the movies is that they're not just moving from east to west, they're moving up and down, tracing out what's called a Rossby wave. We have these on Earth as well. In particular, we see them around the poles, there's circumpolar jets, and we can also see them in the jet streams at mid-latitudes.
Jet streams on Earth typically flow from west to east, but sometimes you can see them meandering from north to south, and that's a signature of Rossby waves here on Earth. These meanders can sometimes grow stronger, and that can lead to everyday weather changes, such as the passage of fronts or storms being generated.
For most people, what we really want to understand is weather on Earth, and what are the things that affect weather on Earth. Now, Jupiter and Earth are very different planets. We don't have land and we don't have seasons on Jupiter. On the other hand, we see very similar weather phenomenon. So being able to understand and study another planet teaches a lot more about what's common in an atmosphere on the Earth.
Jupiter's by far the largest planet in the solar system. It has an influence on everything else. So if we want to understand how do planets form, how do solar systems form, we really have to start with Jupiter.
By studying Jupiter, you're going to get one piece of the puzzle. Not necessarily how life formed, but maybe how the ingredients that made up life eventually got spread around in the early solar system and got to us.
We care about the light elements because that's what we're made out of. We've got a puzzle about where these volatile elements, these lightweight elements like nitrogen, carbon, noble gases, where they came from.
To determine how much water is in Jupiter is essential to understand how this planet came to form and then how it influenced the formation of all the other planets in the system.
When the Earth formed, in the absence of Jupiter, it probably would have gathered very little water and organic molecules, which would have been concentrated in the colder outer part of the solar system. What Jupiter evidently did as it formed was to scatter cold material that contained water ice and organic materials to the inner solar system, where it could be captured by the Earth and the other terrestrial planets.
We learn about the origin of the solar system. We're learning about our own origins. We're learning about how life comes to be, about who we are and what our place is in the universe. It's about knowledge and about humanity's quest to understand. For me, that's why we need to study Jupiter and the solar system and almost everything.
My name is Bridget Hessman, and I'm a planetary scientist at NASA's Goddard Space Flight Center, and I study storms on Saturn. A great white spot is a massive storm system that erupts on Saturn about once every Saturn year. The great white spot that erupted in December 2010 first presented itself as this fluffy white storm cloud that popped up in the northern hemisphere. The storm, when it erupted, sent large waves up into the stratosphere, and we saw effects like an increased amount of ethylene, something we never expected to see. In the coming days, the winds on Saturn sheared the storm in both directions, and it wrapped all the way across the planet. If you were to scale that to a storm system here on the Earth, what you would have is a storm system that covers all of North America but wraps around the entire planet. There'd be no escaping this storm system, and it would be lasting for a very long time. This great white spot happened to occur 10 years before we expected it, which was very fortunate because we happen to have a spacecraft called Cassini in orbit around Saturn. And that spacecraft has a full suite of instrumentation that allows us to study this over all wavelength ranges. Some of the effects that we got to see in the infrared were these two bright beacons that started to shine right after the storm erupted in December. Those beacons at first showed temperature differences of about 20 Kelvin, which is reasonable for a storm. However, as time progressed, we started to see even larger temperature changes. By May 2011, the two beacons had merged into one, and we saw a temperature change of over 80 Kelvin from the quiet conditions before the storm. So that would be like going from the depths of winter in Fairbanks, Alaska, to the height of summer in the Mojave Desert, all in one storm system. Can you imagine what that would feel like, sitting on your deck? We'd never before been able to study a storm system of this magnitude in the infrared, so we are very fortunate at this time to have a spacecraft in orbit allowing us to make a historical record of this great white spot.
NASA's Kepler telescope trails behind Earth in its orbit. Since 2014, Kepler has been looking outward along the ecliptic, the plane of our solar system. In this orientation, the telescope can observe the superior planets like Neptune, which passed through its field of view in late 2014 through early 2015. As we zoom in to Kepler's array of detectors, we see the images taken by the telescope during this period, sped up from over 2 months of observations into a matter of seconds. The dot orbiting Neptune is its largest moon, Triton, while the smaller moon Nereid trails faintly to the east. About halfway through the observation, Neptune appears to stop its westward march and reverse course. In reality, Neptune always moves east, but at a slower rate than Kepler. This causes an apparent retrograde motion, or backward step, each time that the telescope laps the planet. The Kepler telescope was originally designed to search for planets in other solar systems using the transit method. When a planet passes in front of its star, it causes a small dip in starlight that can be measured by Kepler's sensitive detector, revealing the presence and size of the planet. During the Neptune observations, Kepler instead looked at changes in reflected sunlight. It measured fluctuations in Neptune's brightness of less than a single percent, caused by factors including the planet's daily rotation, the movement of clouds, and even seismic waves within the Sun itself. By measuring tiny variations in Neptune's brightness, Kepler teased out clues to the planet's hidden dynamics, pushing the limits of its detector and laying the groundwork for more detailed studies of exoplanets in the years ahead.